Assalamu alaikum, dear students. We're back with another video lesson. In the previous lesson, if you remember, we talked about mechanical energy. And of course, we said mechanical energy is the sum of all the types of kinetic and potential energy, of course. Remember, in translational energy, we have kinetic energy and potential energy. But when it comes to rotational motion, we will add rotational kinetic energy as well, because as long as the object is moving or rolling, of course, there is a rotation, and this rotation, of course, will add up to the total energy or mechanical energy here as well. So last time we talked about these equations. We said mechanical energy, of course, is measured in joules. It is a scalar quantity, not a vector. So mechanical energy equal to the kinetic energy or translational kinetic energy plus rotational kinetic energy plus potential energy. And you already know that for translational kinetic energy, it is equal to 1 over 2 mass times velocity squared. For rotational energy, it is equal to, because it is rotation, remember 1 over 2 instead of mass, we have moment of inertia. And of course, because instead of speed, we have angular speed squared. So don't forget this. That is for rotational kinetic energy. And then for potential energy, you're very familiar with this. And of course, this is mgh, mass times gravitational acceleration times the height. All right, and then mechanical energy may be conserved. Yeah. So if mechanical energy is conserved, that is when there is no friction. That is when there is no air resistance, or when these two are considered negligible. Then of course we can say initial mechanical energy equal to final mechanical energy. And if that is the case, then of course the total energy here at the top of this incline will equal to the total energy at the bottom of this incline. But guess what? What do we have at the top of this? Remember, we have only potential. If the object is at rest, then we can say potential energy equal to mgh, but then there is no kinetic or no translational kinetic energy. Why? Because the speed of the object is 0. If the speed is 0, that means kinetic energy of translation is 0. What about rotational kinetic energy? Once again, if the object is at rest, that means there is no angular speed. No angular speed, that means there won't be no angular or rotational kinetic energy. So at the top, like in short, at the top, we will if the object is at rest, we will only have potential energy. While at the bottom here, all this potential energy, that is if the total mechanical energy is conserved, all this potential energy will convert to translational and rotational kinetic energy. And the potential energy at the bottom would be 0. That is because the height of the object here at the bottom is 0. All right, and then kinetic energy of rotation. You know the equation, yeah? 1 over 2 times moment of inertia times angular or final angular speed square. And then for translational would be the same, but remember the translational quantities, and that is going to be 1 over 2 times the mass times velocity squared. And of course we said, but there is one more thing you need to know, all right? So when an object starts rolling down from the rest without slipping, there is the condition here, okay? So we have a condition. Whenever it says without slipping, that means we will have potential energy on the top of the incline, let's say, and then of course we will have rotational and translational kinetic energy at the bottom. But what if they said if the object is slipping? That is a different story, or it could change the situation completely, because if it says the object is slipping, that means the object would be falling, or the object will be considered as a free fall object. And when it comes to free fall object, we will have no rotational kinetic energy. I'll explain this better in a second. So in this case, we said if it starts at rest, so the translational kinetic energy, rotational will be 0, and then at the bottom potential energy will be 0. And of course we discussed all this, and then we said at the end we'll have initial potential energy will equal to the final translational kinetic and rotational kinetic energy. And now let's talk about this study tip, yeah? So now we have it says on a smooth slopes, or when object experiences slipping. This is very important. So remember, we said when the object experiences slipping, what will happen here? Now bear with me. So let's say here's the incline, okay? And here's the object if it is falling down, let's say, and the object is slipping. Slipping here, that means the object is not rotating. So what happens in this case? If the kinetic or mechanical energy is conserved, so let's say this is initial, right? Mechanical energy, initial mechanical energy will equal to final mechanical energy here. Let me use M capital better than this. Mechanical energy, you can say final here. But look, at the top here, do we have kinetic energy? If the object is at rest here, then of course there is no kinetic energy. So we can say, once again, mechanical or initial mechanical energy, let me rewrite this one, equal to final mechanical energy. That is in case of, let's say, slipping here. So final. All right, final mechanical energy. But for initial, we will have, right, potential energy plus kinetic energy. This, in this case, is going to be translational kinetic energy, because when it says in case of slipping, there won't be no rotation. All right, and then of course these are initial, you can say, and then equal to final potential energy plus final kinetic or translational kinetic energy here. So these are final. But for initial, of course, what do we have? We have mgh, or you can say height 1, all right, or initial height, and then plus kinetic energy, translational in this case, which is going to be 1 over 2 mv squared. This is initial, equal to final potential energy, which is mgh final, you can say, and then plus 1 over 2 mv final squared. Take a look here. When the object is at rest, okay, that means there is no speed in here. If there's no speed in here, this part becomes 0, yeah? So of course now we will have only potential energy. What about at the other part when it comes to the bottom of the incline? So the height will be 0. If the height is 0, that means this part is 0 in this case. So we can say the initial potential energy here will equal to the final translational kinetic energy. So in this case, let's rewrite this again. So we can say mgh, right, equals to 1 over 2 m v squared, that is the, or final v squared, yeah? And then if we want, by the way, we have mass of the object at both sides, so these two will cancel out. So if we want to find the translational speed at the bottom of the incline, so v final, let's just call it, okay, go ahead with v final, that is all right, equal to 2 times what? 2 times gravitational acceleration times the height, but we want the velocity or the speed at the bottom of the incline. So in this case, we can say v equals 2, or final speed, let's call it. By the way, when we say velocity, we include the direction as well, but when we say speed, we just care about the magnitude. So we'll just go ahead with the speed here because we just want the magnitude of the velocity here. So final speed here will equal to the square root of what? The square root of 2 times gravitational acceleration times the height. So I want you to remember this and take a note for this. Okay, so whenever an object, regardless to the shape, if the object is falling or if the object is moving or slipping, don't forget, if the object is slipping, that means the object would be falling under the effect of a free fall acceleration. And in this case, we will only have one equation to find the translational speed at the bottom of the incline, and that is this equation. So once again, regardless to the shape of the object, okay? So translational speed will equal to the square root of 2 times gravitational acceleration times the height of the object. And of course, you can see here that translational speed of the object depends on what? Depends on the height of the object only here, okay? So regardless to the mass of the object, it does not depend on the shape of the object as well. But what if the situation is changed and it says the object is rolling, right? The object is not slipping. And that is, if that is the case, of course, things will change. So bear with me. Let's take a look and see what happens if the object is rolling down without slipping. So once again, here, of course, we will have potential energy. We'll have kinetic energy as well. But if it is at rest, this part will be 0 because there is no speed. There is no angular speed as well. All right. And of course, there is a certain height you can see here. Sometimes there could be a certain angle as well. let's say this angle is 37. All right, then at the bottom here, of course, here's the object, starts to roll down, and here's the object again. And so what happens exactly at the bottom of the incline or of the slope here? So of course, here we will have potential energy, let's say, or what happens to potential kinetic energy as well. So we'll have potential, let's say the potential energy, and we will have kinetic energy. But remember, this potential energy at the bottom will be zero. I'll tell you why. So translational, right? There will be a volume. Of course, there is a rotational kinetic energy as well. All right. So what is the kinetic energy or translational kinetic energy and rotational energy as well? Rotational kinetic energy as well. For the potential energy, of course, at the bottom, because there's no height in here, right? It is level, so we can say that the final potential energy is zero. What about final translational and rotational kinetic energies? We'll talk about that one too. All right, so let's say this is initial potential energy, initial kinetic. All right, assuming that the total energy or mechanical energy is conserved, again, we'll say mechanical energy or initial mechanical energy equal to final mechanical energy. All right, but once again, initial mechanical energy, there will be only potential. Why only potential? Because if the object is at rest, let's not forget this, then there is no speed or angular speed. If there's no speed, then of course both rotational and translational kinetic energies will be zero. So we can say potential energy plus, let me just write down these, translational kinetic energy, all right, and then rotational kinetic energy equals to what? Equals to, again, potential energy. These are initial, by the way, initial and initial. Final potential energy plus kinetic energy of translation plus kinetic energy of rotation. Translation and rotation as well. So these will be final and final, of course. All right, now, remember, at the top, if the object is at rest, this two parts will be 0 and 0. Why? Because this speed here is 0 and omega here is 0. What about at the other part? At the bottom of the incline, there is no height, so because the height is 0, that means the potential energy will be 0 here as well. Okay, so let's say 0. Okay, now the next thing is, how do we find the speed at the bottom of the incline? That is a very good thing. All right, so once again, potential energy, that is mgh, we can say initial, equals to 1 over 2 mv squared plus 1 over 2, by the way, for rotational, instead of m, we'll use I, instead of speed, we'll use angular speed, yeah? Very, very good. Now, but take a look here. This I, that is the moment of inertia of the object, this I depends on the shape. Imagine if we have a ring that is rolling down, yes? So if it is a ring, what is the moment of inertia of a ring, yeah? Of a ring, that is, of course, it is mass times radius squared, yeah? Okay, so now, let's plug in these numbers and see what will happen to our equation. That is a ring as an example, yeah? All right, so once again, mgh, that is initial, equals to 1 over 2, all right, mass times velocity squared, or speed squared, let's say, speed squared, plus 1 over 2, and the moment of inertia of a ring equal to what? Equal to mass times radius squared. I can use r small for radius here, because so that we can cancel this out later. And then omega squared. What is omega squared equal to? We know that omega equals to speed over the radius, yeah? So I can just plug in here, but it is omega squared, so it becomes speed squared over radius squared. Now you can see here, this radius will cancel out with this one here. So what am I left with? So continuing this, you will see that mgh equals to 1 over 2 m speed squared plus 1 over 2 again, plus 1 over 2 again, and then what is left in here? Only mass and speed squared, yeah? So mass and speed squared. Take a look here. We have mass and speed, and of course there is 1 over 2, so we can add them together, yes? So if we add them together, what will happen? Let me erase or move this one up a little. All right, so let's get pencil back. So in this case, mgh, right, there is half mv squared plus half mv squared. That is going to be 1 mv squared, yeah? Or you can say 2 over 2, and of course it becomes what? It becomes mv squared again. But we want translational speed. Before we go to translational speed, look at the equations both sides. We have mass and mass in here, so they cancel out, yeah? So we can say speed squared equals to what? Equals to gh. But we want speed, not speed squared. So speed equals to the square root of mg here. Not mg, my bad. It is gh, okay? It is equal to gh. So based on this, take a look here. What is, if the object is slipping here, okay? What does the speed of the object at the bottom of the incline depends on? Remember, in this case, the object is rolling. So of course, the object depends on the shape of the object, yes, because that is a different moment of inertia would have a different constant here, a different factor here. And of course, it depends on what? It depends on the height of the object as well. But what if it was, let's say, what if it was, what if it was, let's say, the angular speed? If it is angular speed, we've said it before that angular speed equals to, let's say, velocity over the radius, yeah? So in this case, of course, we can say velocity, that would be the square root of gh over the radius. So we can say it depends on the height of the object, or the height of the incline that the object is falling through, and then the shape of the object, of course, and then the radius of the object as well. And also the translational speed as well, because the translational speed, the radius of the object, the shape of the object, all determines the angular speed at the bottom of the incline. And of course, we can call this one f final, since f initial or initial angular speed was 0 because the object was at rest. But at the bottom, you can see that it will be here. But do you have to go through all this calculation every time? No. Let me show you an easy way so that you can do this without, or you can find whether the translational speed or the rotational speed without doing much of a calculation. What is this? All right, take a look. So here's the rule that you need to apply here. So for example, you're trying to, first of all, you need the moment of inertia, by the way. Okay, so let's say the moment of inertia for the object. And let's say, of course, we will have different shapes, yeah? All right, and then of course we can find, let's say, the translational speed, yeah? Translational what? Translational speed at the bottom of the incline. So how do we do this? But before we do this, first we need, let's say, the equation that you need to use. So basically, here's the equation that we're going to use. It's going to be v, the square root, that is speed, of course. Here we're going to use a fraction here. What do we exactly use in this fraction? In this fraction here is what we're going to use. You have moment of inertia, yes? We'll say 2 times the denominator, and of course over numerator plus denominator. And what do I mean by this? And then of course you will do this. You will insert into the equation, and then you will just write not mg, you will just write gravitational acceleration times the height of the object. Let me show you what I mean. For example, let's say we have a ring, yeah? So for a ring, what is the moment of inertia of a ring? You already know that it is mass times what? Times the radius squared. So what is the factor here? And of course you can say that it is 1, yeah? And of course, can I say 1 over 1? All right, I think I should have started with a disk, let's say, first. So you can see this. The moment of inertia of a disk, of course, it is 1 over 2 times mass times the radius squared, yeah? Now, for the translational speed, we're going to write this equation, yeah? Of course, we're going to say factor plus or multiplied by gravitational acceleration times the height. What about for this factor here that we're going to write? And of course, here's what you need to write. Based on this equation, or based on this rule, it says 2 times the denominator. what is the denominator here? The denominator, you obviously know it is the bottom of the fraction. So 2 times 2, that is going to be what? 4. All right, 2 times the denominator, 2 times 2, that is 4, right? And then as for the bottom here, we'll say numerator plus denominator. So what is the numerator? It is 1. Okay, numerator, that'll be the top of the fraction. It is 1 plus the denominator, that is going to be what? 1 plus 2, it is going to be 3. And this is your equation you need to use. We'll use the same rule and apply for all the other shapes as well. Now let's go back to the ring. We'll write this, right? We'll say a fraction or factor here times gravitational acceleration times the height. But here for the ring, it is just 1. Even the bottom is 1, so numerator is 1, denominator is 1. 2 times the denominator, that'll be 2 times 1, that is 2, right? And then 1 numerator plus denominator, that is 2 as well, so it is going to be 1. So we can say the translational speed for a ring at the bottom of the incline equal to gravitational acceleration times the height. All right, what about other shapes? Is it correct? Does it hold true for all the other shapes? The answer is yes. Let's say this time for a solid ball, yeah? If it is a solid ball, right? If it is a solid ball, you know, what is the moment of inertia of a solid ball? That is, of course, 2/5 times mass times the radius squared. You do know this, yeah? This is called denominator, this is numerator. So the equation has to be, here's what it is, factor times what? Times g times the height. So we'll say 2 times denominator, that means 2 times 5, that is 10, all right? What about for the bottom? The under, let's say the fraction, we'll set numerator plus denominator. So what is 2 plus 5? Of course that is 7. So the translational speed at the bottom of the incline for the solid sphere is going to be 10/7 times gravitational acceleration times the height. Is it true for all the other shapes? Absolutely yes. And this is what we're going to use. So you don't have to go through a lot of calculations, yeah? Just remember this. But in order to do this, by the way, you can memorize this, but in my opinion, I would recommend you, let's say, that always you write the moment of inertia for the object, because that will help you to remember the moment of inertia for each object, and then, of course, it will help you with this and guarantees you that you're not going to make any mistakes. This is exactly what I've just told you about, yeah? But don't forget, if the object is slipping, then it is always 2 times gh, nothing more, nothing less. And that was for shape. You can see here that these are all, let's say, 3 or 4 different shapes, of course, yeah? There is the 4th note, it says, based on the above equation, that is what we have said. For rolling object, it has to be rolling, it has to be rotating, yeah? It is clear that the speed of the rolling does not depend on the mass or the radius, yeah? But rather the height and of course the shape as well, okay? But however, if it is the translation, if it is the angular speed, it depends on, of course we can say it depends on the speed of the rolling, it depends on the height, the shape, and the radius as well, yeah? And of course we said the translational speed as well. So all this doesn't mean anything if I don't solve a question for you. So let's solve a few questions and see how it works, yeah? So there are 2 ways to do this, yeah? First of all, you can see that I've solved here, like for example, with a lot of calculations, but I'm going to use the fast way for you, yeah? And then you will see that this too will always equal to or result in the same answer. So we have, it says, a solid ball with a massive 4.1 kilogram and a radius of this starts from rest at a height of 2 meters. So all what you need, if height is given, all you need to do is, or all you need is basically this 2 meter. And that is the height, yeah? And then one more thing as well, you need the shape of the object. Why? Because we want the moment of inertia for this shape to find the factor so we can multiply by gravitational acceleration multiplied by the height. All right, so bear with me. Let's get this. The height is 2 meters, let's say. All right, so take a look. We said, what is the question? It says, what is the translational Let's remove this on the screen. All right, let's get it back. No. Okay. So what is the question? It says, what is the translational speed of the ball when it leaves the incline? Yes? We said, before we do this, first of all, you need to know the moment of inertia for the object. So we have a solid ball, yeah? So solid ball, that is a solid sphere, you can say. Okay, so here's at the top, the height is 2 meters. The height is 2 meters. Okay, and then what is the translational speed at the bottom of the incline? And that is all what you need. Since it is a solid ball, what is the moment of inertia of a solid ball? Moment of inertia of a solid ball, you already know that. It is, what is it? Yes, well done. 2/5 multiplied by the mass multiplied by the radius square. Why am I writing this? I'm writing this because I'll need this for the factor. So we need this to find the translational speed, yeah? So translational speed equals to, translational speed, we said, let's get this back, let me write it here. Translational speed equals to the square root of, all right, I don't need all this. Let me write it here. Translational speed equal to a factor here, a fraction multiplied by gravitational acceleration multiplied by the height. Do you remember what was the rule? We said 2 times the denominator, numerator plus denominator, yes? Okay, so let's apply this on this equation. So once again, translational speed equal to 2 times denominator, 2 times 5, that is 10, okay, over numerator plus denominator. So 2 plus 7, 2 plus 5, that is 7, right? And then multiplied by what is g? That is 9.81 times the height. What is the height? We said it is 2 meters. Now all you need to do is just do the math, you'll find the answer. Let's get a calculator and see what is the result will be. So the square root of 10 divided by 7 multiplied by 9.81 and then multiplied by 2 meters and then plug equal, you will see that the answer will be 2 or 5.29, and of course because it is translational speed, the unit will be meter per second. And this is how easy it is to find this, yeah? So just using one step you can find the answer without needing the mass, the radius, or even the angle of the incline. But of course, in different situations we might need the angles here. So you can see the answer is 5.29 here. All right, there is a note here, says, note that if the object does not roll, so this is something important, yeah? What will happen if the object did not roll? What would happen if the object was slipping, yeah? In this case, of course, we had only one equation, v equal to 2 times g, gravitational acceleration times the height. That is if the object is not rolling, yeah? If it is just slipping. So the speed obtained while rolling is less. By the way here, there's a very good point here. You can see that if we try to find the speed here without rolling, you will see that it equals to 6.26 meters per second, which is bigger than the speed when it was rolling. When it is rolling, it is 5.29. When it is not rolling, it is 6.26 meters per second. What is the difference, or why is there a difference between the speed of the solid ball when it is rolling or without rolling? And to answer this question is this. The speed here is higher when it is not rolling because while it is rolling, part of this speed will change to what? Will change to the rolling energy, and of course you will see that the speed will be less because of rotational kinetic energy. So we can say the speed here is less because part of the energy as a total will change to the rolling of the ball, so we get a less translational speed at the bottom here. But if the object is not rolling, it will experience a free fall. And if it is a free fall, there's no energy loss here or no energy conversion to rotational. So all the potential energy here will change to kinetic energy there. And of course, the speed here will be 6.26 or 26. All right, moving on to another question here. It says, take a look. This is one of the past paper questions. It says, if a solid ball rolls down from the top of the inclined plane of height of 2 meters. So what is the height? 2 meters. To the bottom of it without slipping. And a second case, so one time without slipping, and then a second case falls down freely from 2 meters high. By neglecting, ignoring resistance, okay, and of course friction as well, the final speed of the ball center, okay, what will happen? Depends on the mass of when it is rolling down? No, because we did not have any mass for the translational, or let's say for the translational speed, not even for the rotational actually. It says the final speed of the center, of the ball center, are equal in both cases. Is it? No, we just said that if it is falling freely, it will be higher. The translational speed, of course, will be higher than if it is not falling, if it is rolling as well. So their translational speed are not equal, of course. It says will be greater when it rolls down. No, because we said part of the total will change, will convert to rolling. So it's not going to be bigger, it will be smaller indeed, okay? And then part D says, or option D says, it will be greater when it falls freely, and this is the correct option. Why? Because we said earlier that part of the total energy will convert to rolling. So as a total, or you can say as a comparison, the translational speed with rolling will be less than the translational speed without rolling. Did I say it correctly? Once again, the translational speed with rolling will be less than the translational speed without rolling. Without rolling, that means falling freely. All right. Now, moving on, we have another question here. It says a 1.5 kilogram bicycle tire. You know that the shape of the object that is rolling or moving, it is very important for these situations. At the end, it gives you a hint. It says, assume that the tire is a hoop with moment of inertia equal to mass times radius squared. That is a very good hint here. So the radius is 0.33 meters, starts from rest, okay, rolls down from the top of a hill that is 14.8 meter high. What is the translational speed of the tire when it reaches the bottom of the hill? So once again, the translational speed at the bottom, right, we can say final translational speed at the bottom as well. All right. Not this. Okay. Let's do this one as well. Remember, we can do all this in one step, right? So we said translational speed at the bottom will equal to the square root of, we need a factor here, a fraction, so we multiply times the gravity times gravitational acceleration times the height, yeah? We said this one depends on the shape, yeah? What is the shape of a bicycle tire? It tells you that consider the shape as a hoop, right? And that is, of course, m times or mass times the radius squared. So we can consider this this to be 1. It is 1 indeed, okay? And of course, we can say the bottom of this one is also 1 as well, yeah? So we can say 1 over 1 so that we can use the equation. We said for the equation, 2 times denominator, numerator plus denominator, okay? So we can say 2 times the denominator, so the denominator is 1, so 2 times 1, that is 2, right? Numerator, that is 1, plus denominator, that is also 1, so we get a total of 2. 2 divided by 2, that is 1 here. So we can cancel out this 2 here together. So we'll say translational speed will equal to translational speed at the bottom. We can call it final 2 as well, by the way, okay? Equals to the square root of gravitational acceleration multiplied by the height. And that is, of course, 9.81 multiplied by. What is the height? The height is, what is the height? It is 14.8 meter. All right, now, do the math, yeah? All right, so let's say the square root of 9.81 multiplied by 14.8, and of course the answer will be 12.04. We could just set questions here. So you can see here 12, right, 0.0, and of course, or you could do the fast way. Remember, I did not even write the factors here because you can see that they cancel out or just 1. And then all you need to do is just plug in the numbers and you will get the answer. All right, now here we have a different situation here. I want to pay close attention here because we have a slightly different situation than the previous one here, and I'll tell you what it is. Okay, what do we have here? It says a regulation basketball. So we have a basketball, yeah? And remember, in terms of the moment of inertia of a basketball, that would be a thin spherical shell. And of course, the moment of inertia in this case is going to be what? Yes, what is it? 2 over 5 or 3? 5. You said 5? 3. Okay, very, very good. So let's see what is different in this case compared to the previous ones. All right. Let's move this one down a little bit. Okay, here. And that is all what we need. Take a look. It says, so we have a basketball that has a 25 centimeter diameter. Don't forget, that is diameter, okay? Maybe approximated as a thin spherical shell. That is also a very good hint. How long will it take the basketball starting from rest to roll down without slipping 4 meters down an incline that makes an angle of 30? So this time, we don't have the height directly. What we have is this, okay? So we have the length of the incline. Remember, not the height. The length of the incline is, so we can say delta x is what? Is 4 meters, okay? Remember, this is not the height. And that is what is different from the previous one. An incline that makes an angle of 30 degrees. So we have an angle of 30 degrees with the horizontal, okay? So this height here is unknown, okay? So you need to find the height, then of course you can use the equation that we've used previously. All right, so how are we going to do this? You've studied this in math. If I want to find this, you can see that I have the angle, I have the hypotenuse, right? This is called opposite. In this case, it is the height, and this is called adjacent, yeah? So how can I find, or should I use sine or cosine? And of course, that is sine. Sine of the angle equal to opposite over the hypotenuse, yeah? All right, so let's do this, all right? So we'll say sine theta. Why am I using sine theta? So that I can find the height, because the height is unknown here. Once again, so you cannot use just 4 meters here, right? Because that is different than the height. All right, so sine theta equals to what? Equals to hypotenuse, all right, divided by the, my bad, okay? Opposite over hypotenuse equal to what? Opposite, all right? Opposite over hypotenuse. All right, so now what do we have? We have sine 30, all right, equals to. The opposite here is representing the height. And of course, the hypotenuse represents delta x. So now how are you going to find the height? You can use cross multiplication, correct? So we can say height here equals to delta x, right, sine 30. So what is delta x? It is 4 times sine 30, of course, equal to half, yeah, or 0.5, you can say. So 4 times half, that is going to be 2 meters in height. So here's the height. Now, what is the next part, right? Don't forget. So that is the major part. If you know this, the rest is easy. Again, why do we need to do this? Because the height is unknown. The question says, how long will it take the basketball, yeah? So we want the time here, delta t. So let me erase this, all right? Now, in order to know how long it takes, of course, I need to find the translational speed at the bottom of the incline. So translational speed equal to the square root of a fraction times g times the height, okay? But remember, it says a basketball, which is a thin spherical shell. What is the moment of inertia of a basketball? Yeah, of course, that was what? That was 2/3 mass times the radius squared. Why am I using this? Because I need this factor to plug in numbers here. So we say 2 times denominator, 2 times 3, that is 6. And then 2 plus 3, numerator plus denominator, that is going to be 5 in this case. Okay, so now plug in the numbers and do the math. 6/5 multiplied by 9.81 multiplied by the height. What was the height that we found? It was 2 meters. All right, so in this case, translational speed equals to, translational speed equals to, we can call this one final, by the way, because initial, that'll be at rest while it was at the top of the incline. So using this, 6 divided by 5 multiplied by 9.81 multiplied by 2, we get an answer of 4.85, yeah? 4.85. That is, remember, this is the translational speed, okay? And yes, so meter per second. Okay, let's put this in a rectangle or encircle this. All right, now what is next? The question says, it doesn't want the final speed, yeah? It says how long does it take? So, of course, now we're going to use Newton's law of motion, yeah? So here, we have this, since we have delta x, by the way, we have this equation, yeah? Because it says find the time, yeah? Delta x equal to 1/2 v initial plus v final, right, multiplied by delta t. This delta t is what we're looking for. So plug in the numbers. Delta x, it was here, by the way, not the height. This is delta x, so we're going to use 4 equals to 1/2. V initial was 0 before rolling down. It was at rest. And then V final we found, which was 4.85, and then multiplied by delta t. And of course, delta t here, you plug in the numbers, you cross multiply, so 2 times 4, that is going to be 8. So we can say 8 divided by V final, because that is 0, so 0 plus 4.85, that is same, 4.85. So divided by 4.85. So what is 8 divided by 4.85? 8 divided by 4.85. The answer is 1.649. So by rounding, of course, we can say the answer is 1.65, of course, yeah? That is meter, by the way, since it is delta time, it is in second. And of course, this is how you will find the answer there. So, all right, now let's summarize this real quick. What have we done so far? Because the height was not given, so we used sine and the hypotenuse to find the opposite side, which is representing the height here. After we found the height, we found the translational speed at the bottom of the incline. Knowing the final speed and having the delta x, the distance here, we can find the time, or delta t, which was 1.65 seconds. All right, and using a fast way, of course, that is applicable. So 4.9, you can see here, 1.6, of course, if you take 2 digits here. But then if we use 4.9 by rounding, of course, then you will get 1.65 in this case. All right. Now, moving on, question 29. This question is also very important. If you remember, previously we had 3 objects or different objects rolling down an incline at the same time, of course, yeah? With the same radius and the same mass. A solid of, let's say, a solid 2 kilogram ball of radius, so what is the radius? Radius of 0.5 meters, starts at a height of 3 meters. So the height is given. If the height is given, that means you're safe, you don't have to do the sine thingy. Okay, and rolls down at a 20 slope. And then, of course, another object, we have a solid disc and a ring, start at the same time, at the same height. Both the ring and the disc have the same mass and radius as the ball. So each one of them have the same mass, the same radius, and start at the same time. Okay? Both start at the same height as well. So both the ring and the disc have, okay, we went through this. Which of the three objects will win the race to the bottom if all roll without slipping? So of course we can do this for the solid ball, for the solid disc. Let's keep this in mind. All right. Let's see and calculate which and why, if each, let's say, or which one of these will roll or will win the race. Okay, so the first thing, we have a solid ball. What is the moment of inertia of a solid ball? If it is a solid ball, of course, that is 2 over 5 mr squared, yeah? If it is a solid disk, remember a disk is, I for a disk, it is 1 over 2 mr squared, yeah? What about a ring? For a ring, I equals to just mass times the radius squared. So you can say there is 1 here. Okay, now, in order to find their translational speed in here, let's use a different color. So the translational speed, or the final speed you can say, for the solid ball, remember, we'll use a factor here, or a fraction. We say 2 times the denominator, that is 10 over 7 times g times the height. What about here? Okay, translational speed, 2 times the denominator, that is 4. If you add this two together, that is 3, yeah? G times h. What about for the ring? Of course, if it is 1, there is 1 under, so translational speed, let me write this nicer. Translational speed, all right, will equal to the square root of 2 times denominator, 2 over 2 in this case, g times h, yeah? Now, all you need to do is just plug in the numbers, and luckily, or hopefully, I mean, not hopefully, inshallah, you will get the result without any doubt. All right, so now, so in this case, it's going to be 10 over 7 times 9.81 times the height, which is, what is the height? The height is, I think it's over there. I think I hit the height. All right, I think it was 2 meters. Let's move this. I think I cannot do this. What was the height? All right, the height is 3 meters, yes. So let's get back to this. I cannot scroll down, but I could have done this. All right, so the height is 3 meters. All right, so once again, here you'll do the same thing, 4 over 3 times 9.81 times 3. And then once again here, the square root of, let's ignore the 2 over 2. So 9.81 multiplied by 3. Now, let's calculate the value of each, yeah? And then, of course, we'll find the translational speed at the bottom of each one of these. So the first one here, we have the square root of 10 over 7, and then multiplied by 9.81, yeah, times 3, yeah? What was the answer? The answer is 6.48 meter per second. That is for what? I had the total of these. All right, for the solid ball, all right? For the solid ball. All right, and then as for the solid disc, that is 4 over 3 multiplied by 9.81 multiplied by the height, which is 3 again. The answer will be 6.26 meter per second. Yes. All right. And then for the ring, square root of 9.81 multiplied by 3. We'll get a total of 5.42 meter per second square. These are remarkable results. So, do you remember we said, like previously, when we were talking about moment of inertia of objects? Of course, we said it depends on the shape and the radius and the mass distribution here. We said the solid ball would win the race, would come, would reach the bottom of the incline first. And the reason why here, you can see that the translational speed of the solid ball is the greatest, the highest, which is 6.48 meter per second, and that is the greatest. Then after the solid ball, which one comes second? Of course, the solid disk comes second, yeah, which is 6.26 meter per second, and you can see that it is less than for the solid ball. And then at the end, or the one that comes the last, would be the ring here. And of course, with the speed or translational speed would be 5.42 meter per second. So remember this. Of course, their translational speed depends on what? Depends on the shape of the object, depends on the height as well. But since they have the same height, the same mass, the same radius, then in this case, the shape of the object determines which object, let's say, reaches the bottom first. And in our case here is the dear or the beloved solid ball in here. So the translational speed of the solid ball is the greatest, comes disk after, and then lastly, that'll be the ring. So here's what we have. Okay, now we have a chapter review, or question 30. It says a bowling ball with a radius of 13 centimeter starts from rest, let's say, on the top of the incline in height. So the height is given here. All you need to do is just use this, yeah? V final for this, that'll be using the moment of inertia for what? Moment of inertia of a bowling ball. That is like a solid ball here. 10/7 GH, and then the square root of this, and then you'll get an answer of 7 meter per second, the same idea as the previous one here. All right, once again, it says a solid ball of 240 Newton ball with a radius of this rolls 6 meter down a ramp. So this distance, remember, this is not the height that the object falls from, let's say. This is the distance of the ramp in here. So delta x is 6 meter. If delta x is 6 meter, you're given this angle here, we'll say sine theta here equal to opposite over hypotenuse here, and of course opposite of this angle. Take a look. All right, let's get a different color. Opposite of this angle here, it is the height, okay? And of course the hypotenuse would be 6 meter. You will use this to find the height. Okay, and then once you find the height, you will be able to find the translational speed, okay? And then after that, we can find the angular speed using this equation, V final divided by the radius, because angular speed, you know it, V over the radius. So knowing that translational or final translational speed is 7.1, 7.1 divided by, don't forget here, what we have here is this, the radius is 0.2 meters, so no conversion. Then of course, once you divide the two, you will get 36 radian per second. All right, and then this question here, that is going to be your homework for next. All right, remember this, you try to solve this, and later on we'll try to solve it together. That is it for today's lesson. Keep practicing, and I'll see you next time. Assalamu alaikum wa rahmatullah.